Okay, folks, hello. Welcome to another week of Offsite Learning, our second last week. So today we're starting chapter 16, okay? The notes are in the Google Classroom, our agenda. They look like this. Again, maybe a bit more day-to-day this week. I apologize for that. Not all of the notes are going to be there right now. I'll go through and post them as I do. Same kind of goes for the video lessons this week. Sorry, folks. Okay, we're heading into the home stretch. Let's start chapter 16, all about nuclear physics. Okay, so we begin with kind of a tour of the nucleus. Okay, so when you think about atoms, up until now, you've probably thought about chemistry, right? In chemistry, everything you kind of learn about the properties of atoms and elements really boils down 99% of it to what the electrons are doing. It's mostly the study of electron interactions. Now, the nucleus, that is the realm of physics. Okay, not to say chemists don't work with nuclei, but by far it's more interesting to physicists. Okay, so electrons for chemistry, nuclei definitely for physics. Specifically, nuclear physics comes from the word nucleus, right? Okay, so what's in the nucleus? Well, you know this from chemistry, but we're going to look at it in a bit of a different light in physics. So the nucleus contains two types of particles, and collectively we call them nucleons because they're in the nucleus. They're particles in the nucleus. So we have protons, you know those. Those are an old friend, right? Positive charge of +1, the elementary charge, or positive 1.6 times 10 to the negative 19 coulombs. They have a mass of 1.6726, and that actually goes on further based on our experimental data, times 10 to the negative 27 kilograms. Okay, you can use 1.67 times 10 to the negative 27 kilograms, which is on the back of your formula sheet, unless the question says something different. I'll get into what I mean later. But that 1.67 is rounded. Okay, neutrons, no charge. Okay, they're neutral. Their symbol is N0, whereas protons was P plus for positive. Okay, no charge. Their mass is 1.6749. So you can see they're slightly bigger than protons. For the purposes of chemistry, we can basically treat those as the same. However, in physics, we need to be a lot more precise often. Okay, so this should be review from chemistry, and if you didn't take chemistry, this is even review from Science 10. But the atomic number, Z, on the periodic table, and yes, you have a periodic table, okay, you don't have one on your blue formula sheets, but if you take the one that I've been posting online, that's the one you would get in diplomas. You do get a periodic table for physics. So the atomic number, or Z, Z is the symbol we kind of give the atomic number, tells you the number of protons in an atom of a given element. So for example, if you take a look at your periodic table, you'll see that chlorine has an atomic number of 17. What does that mean? It has 17 protons, okay? And it always will have 17 protons. Saying something has 17 protons and saying something is chlorine is saying the same thing. Chlorine can never have 18 protons. If it did, it would be argon. It can never have 16 protons. If it did, it would be sulfur. Okay, that is literally what makes it chlorine, the fact that it has 17 protons. So below the atomic number, at the bottom of the periodic table square for that element, is the atomic mass. Now in chemistry, we often just leave it as it is because we're dealing with huge amounts of the chemical. And so this fact is okay, that the atomic mass is the average number of neutrons and protons because we're dealing with so many atoms that, yeah, the average is going to kind of be what we need to worry about. Right? However, in physics, we're often dealing with reactions that deal with 1 or 2 or 3 atoms. So we need to be much more specific. We actually need to say, no, I don't care what the average hydrogen atom has. I care what this specific hydrogen atom has, or whatever atom it is you're dealing with. So it's not good enough to just say, oh, the average number of nucleons is fine. So a reminder of what we mean there by average and also by the word isotopes, okay, because the average is based on the relative abundance of each isotope in nature. So the simplest example we can use is hydrogen, because that's the simplest atom. So for example, hydrogen has an atomic mass, you'll see on the periodic table, of 1.01 atomic mass units. We'll talk more about those units later. In chemistry, you use grams per mole. It's actually pretty much the same idea. You're just dealing with bigger amounts in chemistry, so you scale it all up a bit, okay? Anyway, it has a mass of 1.01, as most isotopes of hydrogen contain only one proton. We would call that hydrogen 1. But some contain one proton and one neutron. Hey, is it still hydrogen if it has a proton and a neutron? Yes, because what's the test to be in the hydrogen club? To be hydrogen, it's just one proton. I didn't say anything about neutrons. You can have as many neutrons as you want. As long as you got one proton, you're hydrogen. So some contain one proton and one neutron. We would call that hydrogen 2. And you can guess that is heavier, right? It has more nucleons. Or even one proton and two neutrons, which is hydrogen 3. These bring the average up a bit, but they're so rare, those hydrogen 2 and hydrogen 3 isotopes, They're so rare that it barely makes it budge, right? It's still 1.01. It still sits very close to 1 atomic mass unit, okay? Review of what is an isotope. It's just same number of protons, different number of neutrons. So it's still the same element, because if you have the same number of protons, you're the same element. You can have a different number of neutrons though. Same thing, slightly different form of it, okay? Now, in chemistry class, you learn about isotopes. We tell you they're a thing, and then you never really care about them again, unless the question says, explain what an isotope is, right? That's because different isotopes have almost the exact same chemical properties. Go back to what we said about chemistry being basically the study of electron interaction. Different isotopes still have the same number of electrons, so different isotopes don't really change chemically. However, different isotopes can have very different physical properties, right? And they can therefore undergo different nuclear reactions and have a different stability. All of these things we will get to later. So for this reason, in physics, we cannot use that averaged atomic mass because, like I said, hydrogen 2 and hydrogen 1 may behave the same in chemistry. They will not behave the same in physics. So you can't just say 1.01, yep, that'll cover most hydrogen atoms. No, you need to say, is this hydrogen 1 or is this hydrogen 2? Because the physical properties are going to be different. So in other words, ignore the periodic table masses as they are just averages. So I don't ever want you to say that the atomic mass of hydrogen is 1.01. Nope. You have to figure out the atomic mass of the specific hydrogen atom you are dealing with in some physical reaction, some nuclear reaction. Okay. All right. So we said A was the number of protons and neutrons, right? A being the atomic mass. Z is the number of just protons. How can we figure out the number of neutrons then? Well, we have the number of protons and neutrons. We have the number of just protons. So take the atomic mass, that's protons and neutrons, and take away just the protons. What are you left with? Just the neutrons. And we give that symbol N. Okay, so just a summary of the symbols here, okay? Z is the atomic number. Don't mix that up with atomic mass. Atomic number, and therefore number of protons. A is the atomic mass. That's the number of nucleons, or protons and neutrons. And N is the symbol for the number of neutrons. So far, besides a few little hints of where we're going, nothing actually new from even Science 10. Okay, this you actually kind of have seen a little bit before in chemistry, but it comes up once and never again. So this is not seen as often in chemistry. It's pretty much the only way physicists will represent atoms, or at least one of these ways is the only way physicists will do it. Okay, so in general, you have the atomic mass, A, the number of protons, or the atomic number, Z, and then the symbol of the element. So for example, we could have 14,6 carbon, right? That is carbon with 6 protons, the atomic number, and 14 nucleons. Pop quiz, how many neutrons does this have? Well, it would be 14 protons and neutrons minus 6 just protons, leaving you with 8 neutrons, right? 6 protons and 8 neutrons would give you 14 nucleons. Then, since often what we are more concerned with is the atomic mass anyway, and also because, hey, if this is a C, what other numbers could there possibly be here? Right, just 6. 6 is the only number that can go there. Otherwise, it isn't C, it isn't carbon. If there's a 7 there, it's not carbon, it's nitrogen. If there's a 5 there, it's not carbon, it's boron. So by putting the C in here, it actually kind of makes this seem redundant, right? But sometimes we still put it in. But technically, you don't need that 6 because you know it has 6 protons if it's carbon, okay? How would we say this? Well, out loud, we would say carbon 14, right? That lets you know which isotope of carbon you're dealing with, because you could have carbon 13 that would only have 7 neutrons. You could have carbon 12 that would only have 6 neutrons. Okay, in fact, most carbon is carbon 12. And then even in a lazier way, you could say C14. So essentially, in general form, this is just element and then A, the atomic mass, or X, the symbol, A. So you may be asking yourself, or you may have been asking yourself this since our unit 2. How does a nucleus stay together? It's a whole bunch of positive charges forced to be very close to each other. And as we've seen, the electrostatic force is pretty strong, okay? Protons are a bunch of positives. They should repel. And yes, there's neutrons there, but they don't help. It's not like they're negative and keep everything held together. So they're not contributing anything. Well, maybe it's gravity. Maybe there's enough mass there. Let's see. Let's compare, okay, the strength of the electrostatic and gravitational forces between two protons. And it says there, you don't need the separation distance, even though the separation distance is in both of those formulas. So when you see something like that, you think, okay, I probably am going to be able to cancel something out here. So to compare, we usually do a ratio, right? So let's just see what's the ratio of the electrostatic force to the gravitational force for two protons. Well, it would be, right, KQQ over R squared, Q being the charge of a proton, and Fg would be GMM over R squared. Whoops, that looks like an R. Okay, and aha, there we go. R 1 over R squared over 1 over R squared. The 1 over R squareds cancel, and we're just left with, okay, if you're okay with it, I'm just going to say, well, the charges are the same. The masses are the same, right? We're dealing with two protons here, so we're okay with just saying, right? Because we're multiplying by them by themselves anyway. Those are the same number, and now we can plug in. Coulomb's constant and the gravitational constant should already be giving you an idea of how this is going to go. I got that the electrostatic force is greater than the gravitational force for two protons separated by any distance by a factor of 1.24 times 10 to the 34 times larger. So it's not gravity, okay, right? Those things really, really want to fly apart. Gravity is not doing anything to stop that. Gravity is essentially completely ignorable. That is a 1, a 2, a 4, and then 31 zeros. Okay, so it's not gravity fighting this force. It must be something we haven't even talked about, right? Because that covers all the forces we know. Electrostatic, gravitational, magnetic is really just a different application of the electrostatic. Okay, so it must be something that we haven't seen yet. Something that is attractive to protons and neutrons. What do we call protons and neutrons again? Pop quiz? Nucleons, okay? And very strong, right? Strong enough to overcome this thing. But this force only exists in the nucleus. We don't see it anywhere else in the universe. It's only apparent here inside the nucleus. So it acts over incredibly tiny distances in the nucleus. So physicists, being incredibly creative, decided to call this the strong nuclear force, one of the 4 fundamental forces in our universe. You now know 3 of the 4: strong nuclear, electrostatic, and gravitational. But here's the thing, where's the energy powering this strong nuclear force coming from? For example, electrostatic force, well, that's just powered by electric potential energy, right? Gravitational energy, that's powered by gravitational potential energy. Where is the energy kind of powering this strong nuclear force coming from? Again, energy cannot come from nothing. Law of conservation of energy. The weirder things get, the more we still continue to follow back on the very basics of physics. Don't forget those fundamental principles. So we call it binding energy. We say there's this energy holding the nucleons together. So the binding energy is the energy used to hold the nucleons together, or realistically, how we usually think of it is what energy would it take to completely separate them? Those are the same thing, just kind of said backwards, right? How much potential energy does a book gain if you lift it up? The same amount of kinetic energy it's going to gain if you drop it from that height, okay? How much energy is holding the nucleons together? The same amount of energy you'll have to overcome to separate them. So to give the nucleons enough energy to separate them, right? Well, that's a way of looking at their energy of the nucleons on their own. We've given them that much energy by separating them. And whatever we had to overcome tells us how much energy they used to have when they were part of the nucleus, when they were bound together in the nucleus. So in other words, it represents the difference between the total energies of the nucleons when they are separated and when they are bound together in the nucleus. So the binding energy is equal to their energy on their own, subtract the energy they had when they were together in the nucleus, because that's the energy you had to overcome to do that, right? So that was the energy at play there, keeping them bound. Okay, but that seems like a step around. Where does that energy come from? All I said is, oh, it's binding energy, right? So where does it come from? Well, we're going to start to see something here, okay? So just a question to dip our toes into it. An alpha particle is made of 2 protons and 2 neutrons bound together. So in other words, it is a helium-4 nucleus. Why helium-4? Well, if it has 2 protons, what is it? Helium, right? Automatically. And if it's got 2 more neutrons, well, it has 4 nucleons total, because 2 protons, 2 neutrons, so it's helium-4 with its 4 nucleons. So calculate the mass of 2 protons and 2 neutrons and compare it to the mass of an alpha particle. So what are we on about? Let's see. Let's first do 2 protons, 2 neutrons. So that's going to be 2 times the mass of a proton plus 2 times the mass of a neutron. And from your back of your formula sheet, rounded to 3 sig digs, which will be good enough for this. What we're doing now, okay, you get that it's. Okay, so 2 protons and 2 neutrons should have a mass of 6.68 times 10 to the negative 27 kilograms. Great. Okay, so an alpha particle should have that mass, right? Flip over your formula sheet and look at the mass of an alpha particle. Yep, that's not a mistake. That's not a typo. The mass of an alpha particle with its 2 protons and 2 neutrons is slightly less than the mass of just 2 protons and just 2 neutrons. Okay, so what's going on here? The law of conservation of mass that has been taught to you over the years is great for our everyday, our usual world. However, on the scale of atoms, and actually on the scale of really big things with huge masses, things like black holes, okay, mass and energy are not such easily separable concepts. Okay, it is one of the many interesting consequences of Einstein's theory of relativity, which you don't have time to get super into. Okay, but this idea is called mass energy equivalence. So mass and energy are not really two different things, okay? Or at least they can be transformed into one another. You might not be willing to accept that they're kind of the same thing, two sides of the same coin, but at the very least, you need to accept that they can be turned from one into the other. Maybe mass is not energy and energy is not mass, but mass can become energy and energy can become mass. Pretty mind-blowing, right? So let's circle back to our original question. Where does this binding energy come from? Well, notice when the alpha particle is bound in a nucleus, in a helium nucleus, we have a slightly smaller mass. Guess where that missing mass went to? It went to the binding energy. It became energy. Those 0.03 times 10 to the negative 27 kilograms became pure energy. So the binding energy comes from the missing mass, which the proper term for that, the one you should know, is the mass defect, right? If you have a defect in something, you're kind of missing it. It's your weak point. It's something you're not as good at. I have a defect in drawing hands, as you've all noticed. Okay, so we call it delta M, change in M. It's just the change in M. That's exactly what it is. It's the change in mass when it goes from being nucleon to nucleus, or vice versa. Either way, there's a change in mass there. Might be gaining, it might be losing. Okay, that is the mass defect. So how do we figure out how much mass becomes how much energy? What's the exchange rate between mass and energy? Well, perhaps the most famous equation in physics. Okay, although as it is the most famous equation in physics, you would think it would be written down correctly more often. Okay, it almost is never written the proper way. It's almost always written as E equals mc squared. It's actually the change in energy is equal to the change in mass times c squared, right? Without that mass being changed, without you gaining or losing some mass to energy, there is no energy, right? It's not just you just sitting there with some mass are not pure energy. You could be turned into energy if all of your mass was converted into energy, but it is mass right now, right? And so you need to change that mass. You need to make some of it go away if you're going to get a change in energy. And yes, c is still the good old speed of light in a vacuum. That pops up all over physics. So a quick note on some units we're going to look at for mass, okay? So due to the tiny size of nucleons, the kilogram is not always the most convenient unit. So we often use something called the atomic mass unit, which is sometimes written as AMU. More often, it's just U, okay? It's much more convenient, and it's actually really nice to work with because it's defined as exactly 1/12 the mass of a carbon-12 atom. So one atomic mass unit is 1.66 times 10 to the negative 27 kilograms. This is on the back of your formula sheet. Okay, so sometimes a question will need, so often in nuclear physics, we are dealing with very tiny mass defects, or at least we need to be very careful in making sure there is not a mass defect. So you are safe to use 1.67 times 10 to the negative 27 kilograms if the question says nothing else about the mass of a proton or neutron, okay? If the question gives you the mass of the proton and neutron, and it looks like this, it has more sig digs, yeah, use those ones, okay? Do not use your rounded 1.67. So I'll do a couple examples here, but I'm going to make another video of most of the examples, but let's just do a couple at the end here to kind of wrap it up. New equation, we should at least take it for a little bit of a spin. So the splitting of a U-235 atom, again, What is this? What does that 235 mean? That is the atomic mass, the number of nucleons, protons, and neutrons, right? So that's uranium-235. Causes 3.1 times 10 to the negative 28 kilograms of mass to be converted into energy. So is that M? Not quite. It's the change in M. That has been converted to energy. So that is the mass defect. How much energy is created? Okay, well, this is fun, right? We get to use E equals mc squared. Do you feel like proper physicists? I remember the first time I used it, I felt pretty cool. Okay, so, and it's actually, people think it's a crazy complicated idea, complex formula. It's pretty straightforward to use, right? It's probably one of the easiest formulas you've had in Physics 30. I got 2.8 times 10 to the negative 11 joules. You may be noticing here, C squared. C is already a big number, and we're squaring it, right? So in a little bit of mass, you can actually get a lot of energy out. 2.8 times 10 to the negative 11 joules of energy, no, is not a lot of energy, but 3.1 times 10 to the negative 28 kilograms, that's basically nothing. So you're looking at an amount of energy that is a factor of 17 times more than the mass that went into it. Makes sense, because times 10 to the 8 squared gives you 16, right? So negative 11 to negative 28, that checks out. Okay, fair notice, this is very rare for a question to be this nice to just tell you the mass defect. Usually you just got to figure out on your own, okay? But it's not that bad. You just figure out what's the mass of that many protons and neutrons, and what's the mass that they're telling me it has as a nucleus. So how much energy would be released if you split one alpha particle into separate nucleons? So in other words, take that alpha particle made of 2 protons, 2 neutrons, and split it into, well, 2 protons and 2 neutrons. So you've heard of the whole is more than the sum of the parts. That has never been more true than here in nuclear physics. Although I guess the whole is less than the sum of the parts. Okay, so first let's find the mass defect. And that's just, okay, you need to keep a lot of significant digits here. If you put 1.67, you're going to get the complete wrong answer. So what is the mass of the nucleons? Well, in an alpha particle, we have 2 protons. So we have 2 times the mass of a proton, right? We also have 2 neutrons, so add 2 neutron masses. And then we're going to minus the mass of the nucleus, which we know is, and they didn't give me a long number for an alpha particle mass, so I'm safe to just use the one on our data sheet. Subbing in. And I got that the mass defect is, okay, a very small number, but it's about to get multiplied by the speed of light squared. So you actually might get quite a bit of energy out of this still. So the amount of energy we're going to have created when that mass is destroyed is 4.06 times 10 to the negative 12 joules. That is a more realistic version of what these questions look like. So quick note that I will do this in the example videos, but I just do want to mention it here in the theory video as well. This idea of binding energy per nucleon, how would you get that? Any ideas? What did we just find for an alpha particle? We just found its binding energy, right? Because to hold an alpha particle energy together, you have to convert that much mass into energy, right? To power the strong nuclear force. So we just found the total binding energy for an alpha particle. How would we find the binding energy per nucleon? Well, you would take the total binding energy and divide it by the number of nucleons, right? And then you have binding energy per nucleon. The same way if you have pizza and you want to figure out how many pieces of pizza do you give per student? Well, I'll take total slices of pizza and divide by the number of students. Okay, so I will do those examples in a separate example video. I just want to take one more second here to talk about some other units that seem really weird at first, but they actually do make sense once you get used to it, okay? The main reason that we care about mass in atomic physics, physics looking at the atom, is the energy that is created from it. There's other reasons, obviously, too, but the big one is the energy that's going to come from mass defects. So often, we don't even list it in kilograms or units of mass. We actually list it as its energy equivalence. Usually we use mega electron volts per c squared, but you might see electron volts, giga electron volts, tera electron volts, even joules. That one's rare, but you could see it per c squared, okay? It's just coming from the fact that E equals mc squared, or rearranging, because remember, mass and energy are not so different anymore, right? We understand that now. So if you flip over your formula sheet, you will see physics principle 6, conservation of mass energy. And so we often just think of mass this way, in terms of its energy equivalence. Essentially, you start with your mass in kilograms. If you need to, you can convert it from atomic mass units. Use E equals mc squared to get joules. Hey, that should say change in E, change in mc squared. Then convert your joules to electron volts, and then convert electron volts to mega, giga, tera, whatever you need there. Okay, put it back into E equals mc squared, obviously manipulated for mass though, and then just don't actually divide by c squared. Okay, seems weird, but it makes sense when you start to realize how the mass is really the energy and the energy is really the mass, and usually what we care about is the energy equivalence of nucleons, not necessarily their mass that we think of in our day-to-day conversations about mass. So just a quick one to show you what I mean here. Show that 1 kilogram is the same as that many mega electron volts per c squared. So I don't need to convert from atomic mass units here. It's already in kilograms. Since we're trying to say m equals E over c squared, we need to figure out what the E is. 9 times 10 to the 16 joules, right? So if you converted 1 kilogram to energy, if you converted all of 1 kilogram into energy, you'd be looking at an amount of energy about 10 times greater than the largest nuclear detonation ever, okay? From 1 kilogram of mass. So now we've got our energy in joules. That's the mass equivalence in energy. So we very rarely do it in joules per c squared, and this is asking it for it in mega electron volts per c squared. So we need to convert that to, let's just first convert it to electron volts, then to mega electron volts. That'll be easier. And I say that, but I really just mean let's just split it into 2 quote unquote steps. Now I'll have electron volts. Let's just do that. 1 mega electron volt is the same as 10 to the 6 electron volts. I do recommend kind of splitting it up still, but you kind of see where you're going there, right? If you're on point with your unit analysis. 5.629 times 10 to the 29 mega electron volts. Now we just say the mass then is equal to, too many sig digs, but either way, we showed what we set out to do, right? So it does seem weird at first, but you will get used to it. But it makes a lot more sense this way, because what we care about the mass so often in nuclear physics is not the mass, it's what energy it could be turned into. If you look up most particles that are on the scale of nuclei, you will see that they are all given on Wikipedia or whatever, first in this format, and then they do it just because they kind of have to, they put it in kilograms as well, right? But if you're a nuclear physicist, it starts to work this way, which I get can be weird to wrap your head around it. Okay, so that wraps up the theory video. I'll make a video going through the examples that are on the pages between this page and that page, and you can check the agenda or the Google Classroom for practice that goes with this topic.